Okay, so let's get started. Just close that. All right. So hi, everyone, and welcome to Lecture 11 of ECE3311, Principles of Communication Systems. So today's lecture is going to be interesting. So yesterday in Lecture 10, I said, oh, we're going to talk about AM, FM, PM, all those modulation types. Okay, so that's true. We are going to be dealing with those modulation schemes. But before we jump into those, okay, I'm going to give sort of a quick overview of what's involved, sort of referring to the course textbook, right? Cooch 8th edition. And we're going to look at something that once you develop those waveforms, so we're going to do a quick introduction to a couple of them, like particularly the amplitude modulation and phase modulation. We're going to look at how does the receiver detect the correct point in which to say, I'm going to take that value, right? And it's relatively complicated because as opposed to baseband communications, now we have passband or band pass communications. So we're, first of all, taking it to a carrier frequency. First of all, we need to figure out how do we bring it down to baseband, and then where do we sample that information? Okay, so that's the purpose of this lecture. Okay, so we're going to do a little bit of a recap of Lecture 10 before we jump into Lecture 11. So bear with me, because what I'm going to do is I'm also going to do a quick introduction to amplitude modulation and phase modulation. Okay, and this is, so let's jump into this. Boop. All righty. So here we go. So from Lecture 10, we saw this. We saw that we get our passband signal. Okay, this is V of t, is equal to the real of some sort of mapping of a message signal M of t. Okay, this creates our baseband signal. All right, and then it's multiplied by a complex exponential that effectively modulates it to a carrier frequency. Okay. F of c. All right. So very important. So Cooch, 8th edition. So that's our course textbook. Check out. Okay. Table 4.1. Okay, because this table talks about the various modulation schemes and the mapping between, let's say, M of t and also specifically G of t, like what's the result, and then you basically turn the crank, apply this expression. So this expression is super important. So I put a box around it. This expression's hugely important. All right. So a couple of modulation schemes that I'm going to sort of give a quick introduction to, because you're going to need to know, based on this, how you're going to recover them in this lecture, Lecture 11. Okay. So there's a couple. So there's something called amplitude modulation, otherwise referred to as AM. And this is exactly the same AM as in AM radio. Okay. So AM, right? So my human speech, la 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 la, or music, although music isn't comes out as clear through AM, right? Usually, if you listen to a music station, it's often on an FM radio, and that's a different type of modulation scheme, right? That's frequency modulation. But here with AM, the way this works, right? Let's look at it mathematically. What's our mapping function? So G of M of T, right? AM radios, AM, amplitude modulation, is equal to AC. So that's some sort of constant. So that's an amplitude constant. Amplitude constant, right? Plus 1, and then your message signal. That's it. No problemo. So this is actually super duper important. So first of all, we make the assumption that this is real. This is real. Very important assumption. Super duper important assumption. So what we're effectively doing here, okay, is we're adding 1 to your message. This is kind of important because what I'm trying to do is I'm creating a DC bias, right? A constant that if you add it to M of T, and M of T is some sort of time-varying function, I'm adding 1 to it. I'm essentially raising all voltage levels of M of T by 1. Let's look at it. So let's say here's my time function, M of T. Okay? That's M of T. Okay? If now what I do is I do 1 plus M of T, I might get something like this. Same shape, but now I'm effectively shifting it upwards, trying to make it all positive. Okay? So now what I get is something that looks like this. I hope. Okay? So now this is 1 plus M of T. And then I might want to scale it amplitude-wise. So the AC, 1 plus M of T, depending on the value, right? So if AC is less than 0, I'm compressing the waveform. If AC is greater than 1, I'm expanding it, right? So let me draw this again. Boop. Okay, so now I got this. Cool beans. So now that is, this here is my G of M of T. Here was just my M of T. So that's that mapping process I was talking about. Mapping. And this here is my baseband function, my baseband signal. And that's what I want to modulate. So now what? Now I apply the expression. Real operator of G of M of T, e to the j 2 pi fc of t, folks. Now, let's expand this out. Okay. All right. And now let's use Euler, right? Euler's relation. So what I do is I do this. Cos 2 pi fc of t plus j sine 2 pi fc of t. expand out, expand. All right. Now, apply to real operator. So it's only going to extract out any real components of whatever is contained within the parentheses. So that means this gets extracted out. This, because it's imaginary, is not extracted. Right? So now I have that. Okay, so this is great. So now let's go back to my waveform from before. Right, so let me memorize it. Close enough. So now what happens is the V of t is equal to this thing, cosine 2 pi fc of t. And I have this going on. So let's see. So I have this thing going on. I have whatever that envelope is. And again, my apologies if it doesn't look the same. My memory is not super great. That's my g of m of t. So assume that's what I had from the other slide. Multiplied. Multiplied by a cosine. Plus 1 minus 1. What happens? What ends up happening is this thing. So when you multiply anything by a 1, you get anything, right? So this value here is like, I don't know, like 2.943, whatever, repeating, right? Times 1 is going to be 2.5. But then you also have 0 times whatever the value here is. It's going to be 0. What ends up happening is this cosine function is going to get warped. It's going to get manipulated by the shape here, with the peak values taking on values of gm of t, right? So what's going to look like, it's going to be pretty awesome. What will effectively happen is this, the resulting v of t is going to have a shape, okay, that looks like a cosine. Okay. So let me draw it out. This is going to have the shape of a cosine, like the ups and downs, but it's going to follow some, we're going to call this the envelope, right? So what it will look like is, let me draw this. And then there's a mirror image, because remember, minus 1 times this is going to be the negative version of this, right? So there's going to be a flip side. Oh, shucks. I knew I was not drawing right. Let me try again. There. And inside that envelope, you're going to have the cosine wave shaped. It's going to have the same frequency. It's going to be fc, but its amplitude is going to vary as a function of g of m of t. Beautiful. That is what gets communicated at f of c, right? So that, okay, folks, is what we're doing here. Now, now it's like, okay, my receiver picks that up. So what the receiver is going to look at, okay, at receiver, remember at Rx, you know, also shorthand for prescription, but this is not prescription. This is receiver, okay? What your receiver is going to pick up, it's not. Here we go. It's going to pick up this. It's going to just pick up this. And it's going to say, well, the information I want is m of t. So this is what it wants, right? M of t. But this is what it gets, v of t. That, folks, is where you get the detector. So the detector, effectively, what it translates into is you get v of t. I need to do essentially the reverse process to extract out m of t, right? So how do you do that for am? Well, what do we have? So we have v of t is equal to AC 1 plus m of t cosine 2 pi fc of t. All right. All right. So what do? I need to get rid of that cosine. I absolutely 100% need to get rid of that cosine. So what do I do? What do I do? What do I do? So this is what you do. Multiply by cosine, another cosine, 2 pi fc of t. What? Yes. Yes, yes. Here's why. Okay. AC oh boy. Now 2 cosines? Yes, 2 cosines, folks. Why? Because I'm going to do a little trick. Because Wyglinski is always full of tricks. So this is cos squared. Trig identity time. What is that equal to? Trig. Half plus half cosine 4 pi fc of t. So now we get this thing. Right? Half, right? Correct? Absolutely. And half okay? All right. So now what do I do? So let me highlight this because, and I'm going to highlight. This is super important. So that's step 1. Step 2. Okay. Low pass filter. Low pass filter, LPF. Okay. With, remember W / is my shorthand for with. Cutoff less than, not including. Like you could set any cutoff frequency you want, but it's got to be absolutely 100% less than 2 FC. And reason is, I want to cut out this signal out. Like in fact, I want it much less than this, because here, notice, what does cosine do? It's modulating still. In fact, what I've effectively done is I've taken my original envelope, right, this message, G of t, and I'm modulating it not by FC anymore, but by that trig identity. This is actually 2 pi 2 FC. I've actually doubled the carrier frequency. So if I have a low pass filter, okay, and yet my signals are at minus 2 FC and 2 FC, I've cut it out. So what that translates into is that I filter that out. What passes through? What passes through from that process is this. Now what do? I want to bring it down. I just want to extract out M of t. So what I'll need to do is I need to multiply by 2 over AC to normalize the constant, get rid of the constant, and then subtract off 1 to get M of t, right? So take this thing. Okay, multiply by 2 over AC. Great. Subtract by 1, and that's what you get, right? So that's how you build, that's how you extract out your M of t, right? So, oops. So if we go to the slides, right? This is what we call an envelope detector, right? So the process I articulated, so that's another way of doing that. So another way of doing that is you could do the square law device, but it does effectively the same thing, right? So that's one way if you know so the trick, the reason why I did that, and I can get away with it, is I knew exactly what FC was. If I did not know what FC is, let's go back. Let's go to it. So suppose I take this thing again. Yep. So if I take, and I tried the product detector. What is it again? Yeah, AC 1 plus M of t cosine. And what I do is I do this square law device. So it'll look like this, a little box, square. I've now got this thing squared, so it's AC squared 1 plus M of t squared. And you know what? There's my squared. We know what happens with the trig identity. La, la, la. Cosine 2 pi 2 FC t, right? What happens next? The low pass filter, LPF. Some places also symbolically represent a low pass filter as this, right? Only the bottom bar is actually like crossed out, right? And what does a low pass filter do? Takes out the double frequency term. So what we end up getting is AC squared 1 plus M of t squared times a half, and then use square root in order to recover your M of t, and then the same thing that I talked about before. So that's another way. And this is this technique here. This assumes that you don't know exactly what FC is, right? So what I drew here, I had very absolute clear understanding that FC in this precise moment, I knew exactly what it is. Otherwise, this thing would be toast, right? So if, on the other hand, if I had something like this, cosine 2 pi, and let's say I had fc plus f delta. No, I don't like that terminology. Delta f, yeah, that's it, t. You'll find out if you execute this and multiply it with v of t, you'll not get just a DC term. You're going to get kind of a little bit of a mess, and it's not going to be very nice in terms of extracting out m of t. It's going to be a lot more complicated. But if you use the product approach, product detector approach, which is here, all you have to worry about at the end is square rooting everything. Okay, fine. So this here is called a product detector, right? So this is nice for the reason is no need to know FC at Rx in advance, right? The other approach, you do have what they call a priori. A priori is Latin for like in advance, prior knowledge. So I know that FC and I know exactly what it is without any error, and then I can pull off the thing I first showed. Okay, right. So that's the first of the two detectors. Now the second, i.e., come on, boop. Let's look at that. Okay. Oh, sorry. Sorry. This is the envelope detector, right? Because we're trying to extract out the envelope. Product detector is the following. Sorry, folks. I'm just messing up terminology today. Okay. So this is just a summary of what I just described. Now, product detector is a little bit of a different thing. And this is where we use it for things like phase modulation. And we didn't talk about phase modulation. So let's jump into it. Okay. So first of all, phase modulation, or PM. So from table 4.1, sorry, 4-1. Always nice to have the course textbook close at hand. Here we go. So in this case, G of M of T, what is this equal to? How's the mapping set up? The way the mapping is set up here is AC, there's that constant, amplitude constant. But the information, what we saw in AM was all contained in the amplitude. Here, e to the j dp, okay? dp is a constant. AC is a constant. So AC is an amplitude constant. dp is a phase constant. So when we have it in this representation, e to the j, okay, it implies some sort of phase change. But what's interesting is it's going to look like this. It's going to be dp m of t. So whatever signal I had, like that previous waveform, well, holy smokes, it's going directly into the phase term. So this E, as a function of time, this phase changes as a function of n of t. Wow, that's fantastic. So let's plug it in to this guy. Right? By definition, we get that. And so what do we get? What do we get? All right. So what do we get? So we have this thing. AC e to the j dp m of t e to the j 2 pi fc of t. What do I do? What do I do? What do I do? I combine these two exponentials together because they have a common base. So the exponents are going to add, and the base is going to be e. Okay? That's awesome. So what we end up getting is AC e to the j brackets 2 pi fc of t plus dp m of t. Oh, you know this is going to be good. You know this is going to be awesome. Because now what I do is apply Euler again. So apply Euler. And so this is going to be equal to real AC cos 2 pi fc of t plus dp m of t. Very cool. This is my phase term, which I can do that, right? And where am I? Bloop, bloop. Yeah, I could do that. Plus JAC sine 2 pi fc of t plus dp m of t. Oh, that's so cool. Remember, real operator, we don't let that pass. We only extract out this. So at the end of the day, we get this. Awesome. Now, what we need to do is somehow this gets sent over the air, right? So it's a cosine wave. It has a constant amplitude AC, but its phase constantly changes continuously as a function of m of t, which, again, for shorthand purposes, I'm just going to call it that, theta t. So now I need some sort of detector. This is the product detector. So slap my wrists, wrong terminology. This is what I need to extract out from the stream, right? So if we go back to the slides, how does that product detector work? Okay, so product detector, that is what the receiver is going to pick up. You multiply it against this thing, right? So your receiver, right, is going to multiply a cosine wave with a fixed phase, and this is going to be theta naught, right? And here again, we're making the assumption that it knows the carrier frequency of your signal a priori, right? The omega c. Remember, omega c is equal to 2 pi fc, okay? So just heads up. What if you use trig identity here, this thing's going to explode. But what's going to happen is you're again going to get the exact same deal with respect to the double frequency term. You low pass filter that, and what you're left is something like g of t, and then you have that pesky but known theta naught. Theta naught is a constant, right? We can let theta naught equal 0, doesn't matter, right? But as long as we know what that constant phase shift is, doesn't matter. We can always figure out what g of t is. So let's do it. So the process. So if we have Vn of t is equal to AC cosine 2 pi fc of t plus theta t, okay? Now we do this fella. Ay. And then what is it again? Cosine 2 pi fc of t. So again, there's this big assumption that we know exactly what the frequencies are. And then we have theta naught. This is a constant. It's to account for any phase difference between transmitter and receiver. It's a constant. That's also an assumption. And so if you work this out, right, what is this thing? This is a trig identity. This is cos A, cos B. And what is that? Because, you know, I always remember all my trig identities, right? No. Let's see. Trig identities. Up. And hopefully I will find something. There we go. It's going to be, oh, thank goodness. It's going to be half cos A minus B plus half cos A plus B. So expand this sucker out. You're going to get AC over 2. So if we do the first one, what do we get? So these two, the carrier frequency things, are going to cancel out through A minus B. And what you're going to end up getting is something that looks like theta t minus theta naught. Good. That's good. That's good. Happy. And then the second one is going to be cos 4 pi t. This is already looking good. Plus theta t plus theta naught. This, remember, is equal to 2 pi 2 fc. This is my double frequency term, this whole thing. Double frequency term. And like the process indicates, take this and LPF it. LPF application. I'm going to apply it. And what happens is this double frequency term gets canceled out. This passes through. So what I end up getting is this. I get a time varying cosine without a carrier. Minus theta naught. Okay, that's great. That's awesome. But now I need some sort of way of extracting out just the theta, right? So again, what do we do? How do we extract this out? So let's go back to the slide, like, you know, for guidance, the process. Let's see what the process tells us to do. So now I got, and I removed the double frequency term, and I get this thing, right? So what I would like to do, okay, what's the representation here? So the representation is I want to at least get back to the mapping. So we go back to Euler again. So what is this equivalent to, Euler-wise? Well, Euler tells me that this is the real part, and then we also have an imaginary part that won't get considered if we apply a real operator. Right? So this, it's equivalent, that top thing is equivalent to this thing. Right? So far, I've done nothing to change that top equation. Still kosher. Correct? Oh, but wait, Euler says that I can do the following. Absolutely, I can do the following. Totally allowed. Okay, let's take this one step further. I could split this up. And this, folks, and we have to bring the AC back. This is G of M of T. And we just have to reverse map it. Happy. All right. So this lecture, okay? We've stepped through this process of doing envelope detection for amplitude modulation, and we looked at product detection for phase modulation. So the lessons learned here is that we've already applied that very critical expression for V of t, right? The passband signal waveform based on the mapping function of the message signal M of t. And then, very importantly, the ability to apply trigonometric identities, as well as working with the real operator and manipulating the mathematics in order to go between the two domains, right? And also the practicality, right, of using, let's say you get up to a passband, like techniques such as low-pass filters to remove double frequency terms in order to extract out the desired signal, which at the end of the day is at baseband, okay? So in terms of problems that, potentially that can come up, if we look at, let's say, some of the past class tests, okay, like what would one expect, right? So for instance, what one thing could come up is we didn't cover this too much, but like for instance, how do you go from baseband to bandpass, right? Spectrally, when you have a message signal for, say, something like AM modulation, right? And then things like, for instance, drawing the block diagram step by step of how an envelope detector or a product detector would work. All right, so that concludes lecture 11 of ECE 3311. Tomorrow, or the next lecture, depending on how you're watching these, lectures 12 and 13 are the all-important phase lock loop lectures. So that's going to be critical because of things like, for instance, I made this huge assumption about theta 0, theta naught, and whether we need some sort of way of tracking things like any sort of phase variations between the transmitter and receiver in order to establish a lock, as well as, very importantly, any variations in the frequency. So with that, that concludes this lecture, and looking forward to seeing you in the next one. Okay.